All right, so okay, let's start today's session. So, hello everyone, I am Srishi Siddharth. I am a PhD student associated with the Center for Systems and Control at IIT Bombay, and I'm also the TA for this course, Linear Dynamical Systems. So, welcome to the first week's tutorial session. So, let's begin with a very quick recall. So, all right. So, we are going to cover the following topic today. So, the first one is classification of systems. So this includes linear slash nonlinear systems, causal and non-causal, and then finally linear time invariant and linear time varying systems. So after that, we're going to talk about solutions of let's just say LTI and LTV systems. So we'll talk about state transition matrix, that is phi of t comma x naught, and let's see. We'll talk about equivalent state space systems. And yeah, I guess that right. And then realization for LTV systems. So these topics, uh, the screen's not okay. One second, let me try again. I'll just connect once. Okay, yeah. Uh, now I think it is okay. Yeah, I think it's yeah, it's another screen, I guess. So yeah, okay, yeah, all right. So these are the four topics: classification of systems, solution of LTI and LTV systems, equivalent state space systems, and realization for LTV systems. So these topics were covered during this week. Now let's begin with the questions. All right. Okay, so let's go ahead with question number one. So this is a simple question. So comment whether the following systems are causal slash non-causal, and then also comment on linearity. So the first one is yt equals cosine of ut. So u is the input here to the system and the output is cosine of the input. Alright. So the property of causality is simple. The output just depends on the current input at time t. So the system is causal. And to check whether the system is linear, let's say that we have two inputs. So let's consider inputs u1 of t and u2 of t. And the output due to these inputs are y1 and respectively y2. So this is due to u1 and then we have a net input. So let's say this is u3 of t, which is u1 plus u2. And then let's check what is cos of u3. So I think you can guess from right here that it's a non-linear system because this is certainly not equal to. So therefore we can conclude that the system is non-linear. Alright, so this was for the continuous time case. We have another example. So let's look at that. This is a discrete setting. So yn, or if you can also use this kind of a notation. So output at the nth time instant is equals to n times the input at nth time instant. Again, this system is causal because the output just depends on the current input and not on any future time instance or input. And what about linearity? Is the system linear? So again, we have y1 and similarly y2. And due to the combination of the two inputs, we have, sorry, which is exactly equal to y1 plus y2. And here. So this implies that the system is linear. Alright. So now we'll just revise what was the LTI and LTV systems. So what we're specifically talking about is the linear case. So x dot equals 80 xt. Let's say that this also has a time argument plus pt u of t. And then we also have an output equation which can also be time dependent. So this is okay. So this is the most general case that we are going to deal with, and this is the linear time varying system. And if these matrices A, B, C, and D of appropriate dimensions are constant, that is, they do not change with time, then this is an LTI system. So x dot, let's rename this A, which is no longer an argument, which no longer has an argument of time, and similarly this constant matrix. So this is LTI. So linear, because you have already seen, you can have two outputs, y1, y2, and the summation of u1 plus u2 would give you y1 plus y2. Time varying and time invariant in the sense that these are either dependent or independent of time. Alright, now let's look at the next part. which is solution of an LTI system. Okay, so let's just revise a bit first. Uh, so you have the system, the LTI system. The solution to this is, for example, for the homogeneous setting. The solution at any time t is e to the power at times x0. So we are going to consider time. The initial time is 0, and then we are going to consider solutions for t greater than or equal to 0. And then similarly, we have the complete solution due to the input also. So I'll just write that down. Just 1 second. Uh, yeah. So non-homogeneous case. So this is the differential equation. X dot equals axt plus but. Yeah. All right. Just let me know if the screen is not visible. All right. So in this case, the solution to this differential equation is x at any time t is a to the power t x naught plus 0 to t e to the power a t minus tau b tau u tau d tau. So tau here is a dummy variable, and we have the initial time as 0. In case the initial time is some t naught, then this becomes x at t naught, and the integral runs from t naught to t. This remains the same. Alright, so if this is clear, let's move on to the question. Okay, so there is an RLC circuit. So we have the basic one. This is a series RLC. So let's say that this is some V, and we have to find the current in the circuit given the state space representation. So what we have to do is find the state space representation and then find the current. Okay, so the parameters are, the resistance is 1.5 ohms, L is 0.25 henries, and capacitor is of 0.5 farads. The input V is 3 volts. So the question is to find the current, the transfer function of the system, then the zero state response, zero input response, and if we have these two, then the overall response. Alright, so to begin with, let's see what the states of the system are. So we have two elements which store energy. We have the inductor and the capacitor. So the states are the inductor current I at t, which is exactly equal to the loop current. We have to find this, and the capacitor voltage Vc. So let's say this is our state x1 and this is x2. Alright, so let's form the equations first. So applying KVL, so this is simply 3 equals, then we have L x1 dot, so that is di by dt, and plus x2. This is the voltage across the capacitor. This is equation 1. And okay, so let's say that this is u of t. So this implies, just one second. Yeah, so this implies that the derivative of the first state is simply, uh, let's see, so u by r, let's write it in a compact form. So minus r by L x1 plus 1 by L x2, sorry, minus x2 and plus 1 by L u of t. Okay, and let's just substitute the values for the elements. So 0.25 x1, then we have 0.25 x2 and plus 1 by 0.25 to 3 volts. Okay, so this is the first differential equation for the first state. And now we need the differential equation for x2. So we need x2 dot. So this is just a relation for the capacitor. So we have I going through the capacitor is C dVc by dt. This implies that x1, which is the loop current, equals C times x2 dot, which implies that x2 dot is simply 1 by C over x1, and C is 0.5. Alright. And let's say that the output is y of t, because we need to find the current. So yt is the output, which is exactly equal to x1. So this is 1 0 times x1t x2t plus 0 times input. So this is C, this is D. Now we need to find the matrices A and B, and we can do this from equations 2 and 3. Alright, so let's just write down this quickly. x1 dot x2 dot equals minus 6 minus 420. You can check if this is correct, plus 12, I guess. This is 3 volts, and this is 4. Yes. And y is simply 1 0 x1 x2. Okay. So we need to find the current or one of the states. So we need the solution of the system. But before that, let's look at the transfer function. So transfer function, as you can recall from this week's lecture, is given by g hat of s equals c si minus a inverse b plus d, and this is 0. So let's find out the inverse of this matrix. So si minus a is A matrix is -6, -4, 2, 0. This is S plus 6, 4, -2, and S. Alright, so the inverse of a square matrix of dimension 2 is pretty simple. So Si minus A inverse is 1 upon determinant of the matrix. So S plus 6 plus 8. So we switch the elements on the main diagonal, and this is just negative of the element. So 2. So this is S square plus 6S plus 8, S minus 4 to S plus 2. Alright, so this becomes C, which is 1, 0. Let me just get the denominator out. So 1, 0. S minus 4 to S plus 2. And then B is 4, 0. So I'll just write this down. So this is S and minus 4. Let me just get the first elements of every column, and then 4 and 0. So this becomes 4s. Alright, so this is the transfer function. And then we have to find out 0 state response, 0 input response, and the overall. So to find the solution to the LTI system, we need the state transition matrix, which is e to the power at. So e to the power at is simply Laplace inverse of Si minus A inverse. So we have just computed the inverse. Let's just go back. Yeah. So Laplace inverse of this matrix. S square plus 6S plus 8. S minus 4, 2, and S plus 2. Okay, so we have actually three kinds of expressions, and we need their partial fraction expansions. So I'm going to write this down. So we have first is Laplace inverse of 1 upon S square plus 6S plus 8. Then we need Laplace inverse of actually just S over S square plus 6S plus 8. Okay, so let's see. So square plus 6S plus 8. The roots of the denominator equation are S plus 4 and S plus 2. Let's just check. Yeah, okay. So for the partial fraction expansion, we can write this as a constant over S plus 4 plus K2 over S plus 2. And the way to find K1 and K2 is very simple. So K1 is actually 1 upon S plus 4, 1 upon S plus 2 evaluated at S equals minus 4. Sorry, minus 2. Okay, so just what we can do is just take the S plus 4 here. Yeah. So this is just minus half. And similarly, K2 is S plus 2 over S plus 4, S plus 2 evaluated at S equals minus 2, which is half. Then we have Laplace inverse of minus half over S plus 4 plus half S plus 2 And these are the usual expressions. So minus half e to the power minus 4t plus half e to the power minus 2t. Okay. And similarly, we have another expression which has s in the numerator. So we have s over s square plus 6s plus 8. So this is s plus 4, s plus 2. So we can do this because the degree of the numerator is less than that of the denominator. So k1 is simply s over s plus 4, s plus 2 times s plus 4 evaluated at s minus 4. Okay, so this becomes minus 4 and minus 2. And then similarly, k2 would be, you can check this, so it's s upon s plus 4 at minus 2. Yeah, so this is 1 minus 1. Let me just check once again. So k2 becomes s over s plus 4 minus 2 and alright. Okay, so we have Laplace inverse of 2 over s plus 4 minus 1 over s plus 2. So we have 2s plus 4. Alright. So this is 2 times e to the power minus 4t minus e to the power minus 2t. So we just have to find the Laplace inverse of these two expressions, and we have e to the power at as, okay, so let's write that down. Alright, so the first one is s over s square plus xs, so that becomes 2 e to the power minus 4t e to the power minus 2t. The next one is just minus 4 upon the expression which we had first time. So minus 4 minus half e to the power minus 4t. So you can just multiply by minus 4 and take it inside, and then we have, okay, so twice of that. And the last one is uh, so plus twice of minus half e to the power minus 4t plus half e to the power minus 2t. So you can simplify this, but this is the state transition matrix. Alright. So we have to find the zero input response, which is nothing but the solution to the homogeneous case, and that is exactly equal to xt equals e to the power at times x naught. So let's assume some initial conditions. So e to the power at, the matrix given here, times an inductor current. So let's say it's 1 ampere and some 2 volt voltage across the capacitor. Sorry, there's no dot. So this is the solution to the homogeneous case, the zero input response. So let's say Zi. Okay. And now to find the zero state response, we have to do is, I'm going to denote that. Okay, sorry, this is, yeah, all right. So zero state response is Zs. is Laplace inverse of C times Si minus A inverse B S. So we have D equals 0, so we're not going to consider that. So let's assume that we have the step input, which was something like this, 3 volts. So US is simply 3 over S. So the zero state response is YZS equals Laplace inverse of. So we have already computed C times Si minus A inverse B while computing the transfer function. So let's scroll up. Yeah, this is 4S 4S upon S square plus 6S plus 8 times 3 over S. So this cancels out and we have simply which is 12 times. We have already computed this expression also. So it's minus half e to the power minus 40 plus half e to the power minus 20. Okay, so this I'm going to say is the zero input. Let's say that. Okay, so this was just x of t, and the zero input response is x1. So this is 1 0 times e to the power 80 times the initial value. So we have yzi and yzs. So the overall response at any time is just the sum of these two. So at some time t. Alright. So let's see if I've got everything. Uh, so we have the zero state response and the input response. We have the overall response, and that is nothing but the loop current IT. Alright. So I'm going to just pause for a few seconds, and if there are any questions, just let me know. Okay, if not, then let's move on to the third topic, equivalent state space systems. So let's recall first. So you can recall from the lecture notes that algebraic equivalence is equivalent to saying that the eigenvalues and the transfer function of the two systems are same, and then we have zero state equivalence, which is true if only the transfer function of the two systems are same. Alright, so we are going to look at two questions which will clear these statements. So let's say this is question 3. Alright, so show that the following pair of systems are zero state equivalent but not algebraically equivalent. Alright, so this is the first part. So the first system is a second order system. So 0, 1, the identity matrix plus 1, 0, u, and the output is simply the first state. And the second system that we're considering is x dot equals 1, 0, 0, 2 plus 1, 0, u, and y is still the first state. Okay, so let's name these first. So let's say the first system is denoted by A, B, C, D, 0. And the second system is denoted by A bar, B bar, C bar, and D bar, which is 0. Okay, so we have to find the eigenvalues and the transfer function for these two systems. So let's start. So G hat of S is C times Si minus A inverse times B. Just note that D is 0. Okay, so Si minus A is S minus 1, 0, 0, and S minus 1. So Si minus A inverse is simply, this is just a diagonal matrix. So 1 over S minus 1, 0, 0, and 1 over S minus 1. So you can just check this. The denominator polynomial is simply 1 minus, 1 upon S minus 1 whole square. And then you can just divide by these elements. Okay. So then G hat of S is 1, 0. And then 1 over S minus 1, 0, 0. 1 over S minus 1 and 1, 0. So we simply get 1 over S minus 1. Okay. Then we also have the second system. So let's compute the transfer function for that. So let's say this is G bar of S, which is C bar Si minus A bar inverse times B bar. So now we have Si minus A bar is simply S minus 1, 0, 0 and S minus 2. And Si minus A bar inverse is, let's see. So these are just zeros and we solve these. So then we get 1 over S minus 1, 0, 0 and 1 over S minus 2. Okay. Now let's compute the transfer function again. So then C is still the same and B, yeah, okay. So 1, 0, 1 over S minus 1, 0, which is simply 1 over S minus 1. So this implies that the two systems, so the systems are defined by A, B, C, D, and A bar, B bar, C bar, D bar are zero state equivalent. So to comment on whether the two systems are also algebraically equivalent, we need to find the eigenvalues of the system. So just eigenvalues of the system are the roots of the characteristic equation. So this is actually the determinant of the which is the determinant of the resolvent matrix. Is the determinant of Si minus A inverse. Okay, so we already have these for the two cases. So for the system A, B, C, D, we have let's scroll up. Okay, S minus 1 squared. So this implies or lambda is 1 or 1. And then for the second system, we have S minus 1 and S minus 2. This implies that. So these are not equal. So this implies that the two systems are not algebraically equivalent. Alright. So we have another case. So this was part 1. Now let's look at this. So both of the systems given above were the same order. So we had a 2 by 2 matrix here and similarly here. Now let's see another example. So the first system is 1 0 0 1 x plus 1 0 times u and y is the first state. And the second system is simply, let's say, x bar dot is x bar plus u and y equals x bar. So x bar is a real number. Okay, so let's say this is the matrix A, B, C, and D is 0. And then what about here? So we have A equals 1, a scalar, B is 1, and C is also 1. D is 0. So this is, let's say, okay, this is bar then. A bar, B bar, C bar, and D bar. Alright. So let's first find out the transfer functions. So the original system ABCD, we have C times Si minus. So let's find out Si minus A inverse. So we have the previous system. This was the same one. So Si minus A inverse is 1 upon S minus 1, 1 upon S minus 1, 0, 0. And G hat of S was simply 1 over S minus 1. Okay, so let's see what is Si minus A bar inverse. So in this case, the identity matrix is just the scalar one. So we have S minus 1 inverse. And G bar of S is C times. So C bar Si minus A bar inverse. So we have all of these are 1. So 1 times. So this implies that the two systems are zero state equivalent. Since their transfer functions are the same, so the two systems are zero state equivalent. Alright, so then we'll talk about the eigenvalues. So you already know eigenvalues of the first system ABCD are repeated eigenvalues at 1 and eigenvalues of A bar, B bar, C bar, and D bar are simply. So just 1 second. Yeah, this is simply single eigenvalue lambda equals 1. So these two are not the same because we have repeated eigenvalues here, even though they are equal in magnitude. So the eigenvalues of the two systems are not the same, which implies that the two systems are not algebraically equivalent. Alright. So I hope this was clear to you, and let's look at other cases now. So we have done equivalence of two systems, solution of LTI system, and properties of continuous and discrete time systems. So now we'll move on to solutions to LTV systems. Alright, so let's first recall them. So the state transition matrix for the LTV systems is not simply e to the power at, so which was the case for the LTI system. So this is the variation of constants formula. So recall. So you have the time varying system and the output. So xt plus dt times u of t. Then the solution is unique and it is given by so just x of t is phi t comma t naught, where t naught is the initial time times x naught plus integral from t naught to t phi t comma tau b tau u tau d tau. So observe that in the case for LTI system, phi t comma tau is simply e to the power a t minus tau for LTI systems. Okay. And if this is the state, then the output is simply c times xt. So ct phi t comma t naught uh, okay, plus ct times the integral plus dt times ut. Okay, and this is a state transition matrix with some properties. So let's look at those. Okay, so okay, so the first one is that if we differentiate this function phi t comma t naught, it gives you back at times phi t comma t naught. So this is a very important property which will also be used in the questions we look at now. And then the second property is So you have a system which starts from S and the same system which goes from tau to S. This is simply right. So you must have seen the diagram in the lecture. So the second argument is the initial time from which the system evolves. So for example, we have a system which starts from tau and we are considering the evolution till time t. So this can also be achieved by going from tau to S and then going from S to T. So this property is actually the multiplication of these two functions. So phi S comma tau. Okay, so let's look at a question. Uh, yeah, question 4. Okay, so consider the following. LTV homogeneous system. So we have the differential equation x1 dot x2 dot and then the states x1 x2 and then sorry, this is the homogeneous case. So this is it. So this is a 0 t times a and a with the initial conditions as z1 and z2. So this a is not a constant. So where a is 2 by 2 matrix, and this means that z1 and z2 are vectors. So let's just see what's the dimension of the system first. So this is square matrix and 2 by 2. Okay, so 2 rows and 2 rows, so this has to be 2 by 2 as well. So this becomes a 4 by 4 system. So this is actually a 2 by 1 vector. This is also 2 by 1. Okay, so the first part is compute x1 and x2. And the next one is uh, compute the system's state transition matrix, which is phi t comma t naught, which is 0 in our case, for the overall system. Alright, so we have to compute x1 and x2. So this means that we have to solve these differential equations. So let's see. The time varying matrix A is A0. It's time varying because we have t here. So we have t again. Okay. Yeah. Alright. So you can see that this has a nice structure in the sense that this is a lower triangular matrix. So what does this mean? This means that in terms of getting the solution of the system, you can find x1 first and then substitute in the second equation to find x2. Alright, so let's see. This is uh, x1 dot is actually simply x1t. And observe that this let's say subsystem is LTI because A is constant matrix, because A is a constant matrix. Alright, so we have already seen how to find the solution to the LTI system. So x1 of t is simply e to the power at. So we don't have to know what a is here, times x1 at time 0. So we know that this is z1. Alright, so let's say that this is I. Now we need to find out what x2 dot is. So x2 dot is simply t a times x1 at t plus a times x2. Just a second, I think, yes. Alright. Okay, so substituting x1 from equation 1, we get that the differential equation is t a e to the power at times z1 plus a times x2. Alright, so this looks like an LTI system with an input u of t, right? So we can write this as a times x2. This is constant, or let's say independent of time, plus u of t. Alright, so in that case, x2 at any time t is simply e to the power at times x2 0. Then we have 0 to t e to the power at minus tau. We're going to say that B is just identity matrix and then u tau. So u tau d tau. Okay, so we have e to the power at times z2 plus e to the power at into e to the power minus 8 tau. Tau a times e to the power 8 tau z1 d tau. Now there is a property of the state transition matrix in the LTI case, which is these two commute. So we have to the power 8 tau times a. So this is e to the power 80 z2 plus, so tau is just a scalar. Let's say it's here, and we have sorry, this is exponential a tau times a z1 d tau. All right, so this is simply, so these get cancelled and we have tau e to the power 80 a z1 d tau. All right, so let's just cut this. So we have this again. So it is e to the power 80 z2 plus 0 to t. We have, let's check if this is correct first. Yeah, alright. So e to the power 80 z1 tau theta. Okay. So observe that this integral is in terms of tau. So 0 to t is in terms of tau, which implies that e to the power 80 z is can be taken out, right? So this is e to the power 80 z2. Uh, this is simply e to the power 80 z1 0 to t z1 sorry tau theta. So now this is easy. This is t square by 2. So this is x2 at any time t. So we have computed what x1 and x2 are. So let's write them down. So x1 at any time t and x2 at any time t. So x1 is e to the power 80 z1, and then we have x2. So in terms of z1 we have e to the power 80 times t square by 2 z1 plus e to the power 80 times z2. Now this can also be written as e to the power 80 times the 0 matrix. So this is going to be of the order 2 by 2. And then we have a e to the power 80 times the scalar t square by 2 and then e to the power 80. This times the vector z1 and z2. Okay. So observe that this exactly looks like x1 x2 equals sum matrix times the initial values. And this is exactly the state transition matrix, right? Because xt is just phi t comma 0 if we are considering t naught to be 0 times x naught. So this implies that the state transition matrix is simply e to the power 80, 0 and e to the power 80. Alright. And let's check if, so there is also a check which you can perform. So compute if it's a, just to check if you have calculated the state transition matrix correctly, that at time 0 there should be identity, because at time 0 we are exactly at the initial condition. So xt is actually phi t comma 0 x0. So at t equals 0 we have identity times x0, which is the initial condition. Okay, so let's just check. You can substitute t equals 0 and we get e to the power a0 identity and then 0 and identity again. Alright, so if this is clear, let's move on. So we have computed x1 and x2 and then also computed the system's state transition matrix. So for t naught, what you can do is change this integral to t naught to t and this to e to the power a t minus t naught. and then you can perform similar calculations to get the phi t comma t naught. Alright, so then we have the fifth question. So what we are going to do is we construct an LTV system from the state transition matrix. So in the previous question, we were given the sorry, state transition matrix. So in the previous question, we were given the system, that is a differential equation for the LTV system, and we were asked to find the state transition matrix. Now this question is opposite to that. So in the sense that we have been given a state transition matrix and we have to find out what the LTV system is. So this means that we have to find the matrix A. So A, which is a function of time. So that is compute a matrix A of t such that uh, the state transition matrix starting from the initial time is 1, 0 e to the power t square minus t naught square by half minus 1. So this is in the exponential, and again we have t square minus t naught square by 2 such that this is the state transition matrix of the homogeneous ODE. X dot t equals AT x. Let's say t. Okay. So let's check if it is a state transition matrix first. So phi t naught comma t naught is, we have 1 0, then 1 again, and 0. So this property is satisfied by this matrix. And now we'll look at a very important property. We have written this down earlier. So the derivative of the state transition matrix phi t comma t naught is exactly equals to A times t phi t comma t naught. Okay. So what we don't know here is A of t. So let's assume that A of t is some matrix. So let's say A1 of t, A2 of t, A3, and A4. All of these are real numbers. So A1, A2, A3, A4, and can depend on time. Alright, so let's compute the derivative. This is 0. This is exponential of t square minus t naught square by 2 times just t. Then I guess 0 again. Yeah. Then e times t square minus t naught square by 2 times t. Okay, so this equals A1 of t, A2 of t, A3, and A4 times the state transition matrix again. So we have 1 0 uh, exponential t square minus t naught square by 2 minus 1 e to the power t square minus t naught square by 2. Alright, so one way we can find out this matrix is to just post multiply by the inverse of this on both sides. So that's one way. Other is we can just find it at the matrix A at time t equals t naught. Right. So if we substitute that, we have substituting t equals t naught in the above equation. So what do we get? We have 0, 0, and then this is just t naught, and again t naught. So the matrix A looks like A3 and A4. And since this is a state transition matrix, this is simply identity. So this is actually equals to A times T naught. And we can also find the inverse of the state transition matrix. So phi inverse T comma T naught is actually phi T naught comma T. So let's check. Um, so we have the determinant. So it's simply e to the power T naught square minus T square by 2. So we can solve these. And the negative sign. So minus e, and then you can post multiply. So what I'm saying is, let's say this is some matrix, so m of t equals a of t phi t comma t naught. Okay, so mt phi inverse t comma t naught, and then be a at any time t. So you can compute the inverse of the state transition matrix, multiply by m of t to get the matrix A. Alright, so then we have the last question. Okay, so let us consider the system given by this time varying matrix A. So minus 1 e to the power 2t 0 and minus 1. So find the fundamental matrix and the state transition matrix. So recall from the lectures that the state transition matrix for the LTV system is not as simple as that for the case of LTI systems. For LTI system, we just had to compute the Laplace inverse of Si minus A inverse to get e to the power 80. But for the LTV system, we have to find out that Piano-Baker series. So the other method to get the state transition matrix for the LTV system is through the fundamental matrix. So let's recall that. Just a second. Okay, so recall. I'm going to write down the slide number. I guess it's slide 27. So the theorem states that let xt be a fundamental matrix of the system x dot equals ATXT. And then the state transition matrix phi t comma t naught is xt x inverse t naught. So what we need to find is this fundamental matrix x of t. So what we can do is, uh, so let's see. So we have step 1. So let's assume some initial conditions for the system. Let's assume that, okay, so first let's look at the structure for the system, then we'll talk about the solution. So AT is minus 1 e to the power 2t, 0 and minus 1. So again we have this nice structure that we have an upper triangular matrix. So what we can do is find x2 first and then plug it in the equation for x1 dot to find x1. Alright, so let's see. Okay, so x2 dot is at any time is simply minus x2 of t. So this is an LTI system, which implies that solution is simply e to the power minus t x2 at 0. Alright, and then we have x1 dot of t, which is minus x1 plus e to the power 2t times x2t. This is nothing but e to the power t x2 0. Okay, so let's assume some initial conditions. So this was step 1. So 2, assume that say x1 x2 at time 0 is, let's say, 1 comma 0. Okay, so if this is the case, then this implies that x2t is simply 0 and x1 of t is simply minus x1. So again we have an LTI system. This implies that, sorry, x1 dot, so x1t is e to the power minus t x1 at 0, and we are considering this to be 1, so this is, so the solution is x1t x2t for these sets of initial condition is e to the power minus t and 0. Okay, so for the fundamental matrix we need to assume two initial conditions which are linearly independent. So let's see that in step 3, let's assume some other initial conditions. So assume x1 0 and x2 0 to be something else. So let's say this is half comma 1. So we can check very quickly whether these are linearly independent. So alpha times 1 0 plus beta times half 1 equals a 0 vector. So the second equation implies that beta is 0 and then the first equation implies that alpha is 0. So these the two initial conditions are linearly independent. Alright, now we need to find the solutions because of the initial condition that we have taken in the current step. Alright, so let's go. So we have again x2t is simply e to the power minus t x2 0, which is now e to the power minus t. Now we substitute this in x1 dot, which is minus x1t plus e to the power 2t times x2t. Okay, so this is minus x1t plus e to the power t. So this is a differential equation, and what we can do is, uh, so we can write this as a sum of two solutions. So this one is the, let's say, complementary function or the solution to the homogeneous case plus solution to the output. So I'm going to write this as the solution to the particular integral. Alright. So for x1 CF, we simply have, sorry, x1 dot equals minus x1 of t, which implies that x1 of t is, okay, let's see, let's not, uh, so let's say that the d operator is d by dt. So this implies that d plus 1 times x1 is 0, right? Okay, so let's see that, let's denote this by, sorry, f, the function of the operator d is d plus 1. Let's see. And then we have, for the particular integral, we have 1 over fd and then this part, e to the power t. So you can recall this to find the particular integral. You can substitute the powers. So we have e to the power 1t, and if the denominator is not 0, we can just substitute that here to get half e to the power t. Okay, so this is the particular integral xpi. Okay, and then for x1, so let's assume that this is some e to the power minus t times a constant. So we cannot substitute the initial condition here because this is just the one part of the solution. So we can write x1 of t as c1 e to the power minus t plus half e to the power t. And now we can substitute the initial condition that x1 at 0 is half to find the constant c1. So this is c1 plus half, which implies that c1 is 0. So x1 at any time is simply half e to the power t. So now we have the complete state solution x1, x2 for the set of initial conditions half, comma 1. I guess yes. So we have x2 as e to the power minus t and then half e to the power t. Okay, so then we have the last step. So we have the solutions to two linearly independent initial conditions. Then we write them column wise. So the first one is, so let's just write this down, e to the power t, e to the power minus t. And due to the first set of initial conditions, 1, 0, we had e to the power minus t and 0. Okay, so let's just check if this is a state transition matrix. So let's see, phi at 0, comma 0 becomes, so this is 0, this is 1, this is 1, and this is actually half. I see. Okay, so let's see, maybe the initial condition is not t equals 0. Okay, sorry. This is the fundamental matrix. So the fundamental matrix X at t is uh, half e to the power t, e to the power minus t, and e to the power minus t, 0. Now let's compute the state transition matrix phi at t comma t naught. This is xt and x inverse t. So you can observe that the determinant of xt is e to the power minus 2t, which is non-zero. So we can take the inverse. So let's find this out. So we have 0, sorry, e to the power minus t, 0, half e to the power t, e to the power minus t. Then we have the determinant. So we switch these and then minus half e to the power t. Now let's see. Let's just write this down as e to the power 2t. Okay, so this becomes e to the power minus 2t. And then we have e to the power minus t times half, which is negative, and this becomes 0. Then we have 0 again, and then we have e to the power minus 2t. So we have the identity matrix. Alright, so this is the state transition matrix. I see. So this has to be computed at t naught. So we cannot simply do that actually. So let's see. So if we assume that t naught is 0, so t naught 0, this becomes 1 and this becomes identity. And the state transition matrix is simply x of t. So we have e to the power minus t, 0, half e to the power t, e to the power minus t. Let's see if this is correct. Alright. What we can also do is consider some other initial conditions which are linearly dependent. Then find the fundamental matrix and then find the state transition matrix using this formula. Alright. So let me just compute this again. So we have 0, this is 1, 1, this is minus half. Okay, so we get e to the power minus t. Then we have minus half e to the power minus t plus half e to the power t. Then we have 0 and 0. We have e to the power minus t. So we can just check this, that phi t comma 0 at t equals 0 is actually identity. You can just substitute t equals 0 here to get identity. Alright, so that's it for today. Let's just look at what we have done. Okay. So we first looked at the properties of the continuous time and discrete time systems. So we looked at two examples in which we saw how to characterize a system as causal or non-causal and linear or non-linear. Okay. After that, we looked at the solution of an LTI system for the homogeneous as well as the non-homogeneous case, and we found out various quantities for a very simple electrical circuit. So we had found the transfer function, the zero state response, the zero input response, and therefore the overall response. So this was an LTI system because the parameters R, L, and C were independent of time. Alright, so we looked at how to compute the transfer function, and we also looked at how to compute the inverse of a simple square matrix of dimension 2. Then we saw how to get the state transition matrix for the LTI system. That is simply the Laplace inverse of Si minus A inverse. And then we found out the zero input, zero state response and the overall response. After that, we looked at the equivalent state space system. So we had two definitions, algebraic equivalent systems and zero state equivalent systems. So we talked about the eigenvalues and the transfer function of the systems in these cases. Then finally we looked at solutions to the LTV systems. So the solution is given by the variation of constants formula, which is this, where phi t comma t naught is a state transition matrix with some properties. So these are the two properties, and this is very important. Okay. So then we looked at a LTV homogeneous system, in which case we found out that the time varying state matrix has an interesting form. It has a dual triangular matrix form, and then we observed that this can be decomposed into two subsystems. So we can find out x1 easily using the solution for the LTI system and then substitute it to find x2. Alright, so these are just computations, and we found out what x1 and x2 were. And to get the state transition matrix, we just wrote it in this one. Alright. Then next we look at how to get an LTV system or how to get the matrix A given the state transition matrix. So this was a state transition matrix, and we were asked to find out the matrix A of T for the homogeneous OD. So we first check if this follows the property of the state transition matrix, and then we use this property. Alright. So after this, we looked at how to compute state transition matrix of a LTV system using the fundamental matrix. So in the first step, we just looked at the upper triangular matrix structure of the system and find out what x2 and x1 should look like. After that, we assumed some initial conditions and find out the solution due to these initial conditions. And in step 3, we assumed a linearly independent initial condition. So you can see that these are linearly independent. And then we found x1 and x2 due to this new set of initial conditions. So after this, we found out the fundamental matrix by arranging the solutions column wise. And then find out the state transition matrix using this formula, xt and times x inverse of t naught. And then we assume that, let's say that the initial time is 0, and then we found out what the state transition matrix look like. And again we checked a very simple property if this matrix satisfies the state transition matrix property only. All right, so that's it for today. Uh, Thank you. Let's end.